This is Andrea Hendricks, and the topic of this lesson is solving systems of equations by substitution. This will be an additional method to solve systems of equations. In the last section we talked about solving by graphing, but we're going to focus on different methods in the next couple of sections. Our goal is the same, that is, we still want to try to find the point of intersection of the lines in the system, and we're still going to have the same types of solutions, one ordered pair, no solution, or infinitely many solutions. The problem is graphing has its limitations, at least if we graph by hand. Like, how could you tell exactly a fractional ordered pair that solves the equation? So this method will give us a way to do it algebraically so that we are very precise. The method of substitution has a few steps that we're going to go through. The first step is that we will solve one equation in the system for one of the variables. Then we'll substitute this expression into the other equation, solve that resulting equation, which will now be just one single variable, and then find the value of the other coordinate of the solution. So let's look at how we can solve x plus 3y equals negative 28 and y equals negative 5x by substitution. So if we look at this system, our first step is to solve one of the equations for one of the variables. And notice that that's actually already done for us in the second equation. The second equation is already solved for y. So what we do now is substitute this expression into the other equation. So in x plus 3y equals negative 28, we're going to replace the y with negative 5x. And notice this is a linear equation in just one variable, so we're going to solve it by combining like terms and so on. So we would have x, 3 times negative 5x is negative 15x equals negative 28. So x minus 15x, remember there's a 1 there, that's a negative 14x equals negative 28. And dividing by negative 14, we get that x has a value of positive 2. Now we're not done there. Remember, we need an x and a y value. That is the ordered pair. And so in step 3, we need to solve for the y. Well, we can go back to one of our equations and plug in the x value that we now know to solve for y. The second equation is easiest because it already is isolating the y. So if y is equal to negative 5x, we get y is equal to negative 5 times 2. Right, that is the value that we just found goes in there. So that tells us that y is really negative 10. So our fourth step, if you will, is to write the solution. So our solution set is the ordered pair 2, negative 10. Now how can I check? If I plug in 2 and negative 10, I should get a true statement. 2 plus 3 times negative 10, which is really 2 plus negative 30, is negative 28, so it checks. Y is equal to negative 5x. If we have y, which is negative 10, is equal to negative 5 times 2, so that is correct. So since that ordered pair checks in both equations, we know we've done our work correctly. Now let's look at another example. We want to solve 3x minus y equals 5 and y equals 3x minus 5 by substitution. So again, if we write down our system and go through our steps, the first step is to solve one equation for one variable, which again, that happens to be done for us. That's not the case in all of these problems. And then in step 2, we're going to replace in the value y, or variable y, the expression 3x minus 5. So you'd have 3x minus, and then in parentheses, we're going to put 3x minus 5. Distributing the negative 1, right, would give us 3x minus 3x plus 5 is equal to 5. 3x minus 3x, those are eliminated, so we get 5 is equal to 5. And I don't know if you remember this from solving linear equations in one variable. When the variables are eliminated and you have a true statement, that means there are infinitely many solutions. So what that true statement here tells us is that there are infinitely many solutions to this system, If you remember what that means, that these two are really the same line. And so the way we write our solution set is it's the set of ordered pairs x, y, such that then we just write one of those equations since they are one and the same. So it's saying every point that lies on the line is a solution to that system since they're the same line. So that only happens if the variables are eliminated and you have a true statement. Now, here's another one to solve 2x plus 8y equals 3. And x is equal to 8 minus 4y, to solve that by substitution. So again, the first step is already done. One of the equations is solved for one of the variables. So then our next step is to replace, now in the first equation for x, the expression 8 minus 4y. And keep everything else the same. So distributing the 2 gives us 16 minus 8y plus 8y is equal to 3. And notice here this is another special case because the 8y and negative 8y eliminate each other. And so we're left with just the statement 16 is equal to 3. And do you remember this? When solving a linear equation on one variable, if you get a false statement there, that means there's no solution. And that means the same thing for our system. So this means really that these lines are parallel and that there is no solution, or we write that as the empty set. So we still see we get one unique solution, infinitely many solutions, or no solution. Here's one to solve. It is a little bit harder than most, probably because it has fractions. X over 5 plus y is equal to 6 over 5, and x over 10 plus y over 3 is equal to 5 over 6. So the best way to solve this is to eliminate the fractions. And so the first equation we can multiply through by 5. In the second equation, the common denominator between 10, 3, and 6 would be 30. So our first equation becomes 5 times x over 5 is just x, plus 5y, and then 5 times 6 over 5 is 6. Our second equation, 30 times x over 10, 10 goes into 30 3 times, 3 times x is 3x, 3 goes into 30 10 times y is 10y, and that's equal to 6 goes into 30 5 times 5 is 25. So here we don't have it in the form where one equation is already solved for one of the variables. Okay, so now we have a system where we don't have one of the variables isolated. So we've got to isolate one of the variables in one of the equations, and it doesn't matter which one we choose. Since the first one contains just an x by itself, that's actually the easier one to use. So if we first solve the x plus 5y equals 6, for x, we would get x is equal to 6 minus 5y. And then we substitute that into the second equation in place of x. So in place of x, we're going to have 6 minus 5y, then plus 10y is equal to 25. So distributing, we get 18 minus 15y plus 10y is equal to 25. So combining like terms, we get 18 minus 5y is equal to 25. Okay, and now what we need to do is subtract 18 from both sides. So we get negative 5y is equal to, what is that, 25 minus 18 is 7. So solving for y, we get negative 7 over 5. So it's okay to have a fractional value. What we would do now is to solve for the x coordinate, since we already know now what the y coordinate is. So we're going to put this back into one of the equations that doesn't have fractions. So if we use x plus 5y is equal to 6, we will get x plus 5 times our value, which is negative 7 over 5. It's equal to 6. Unfortunately, this simplifies nicely. The 5's divide out, so we get really x minus 7 is equal to 6, or we can add 7 to get x is equal to 13. So the solution to the system would be the ordered pair 13, negative 7/5. Okay, and you can check that as you go through, and plug these 2 points into these equations and make sure that you get a true statement. Okay. Let me just do one last example again where you don't have a coefficient of 1 on either of the variables, just to show you that. So if you have something like 2x plus 3y is equal to 6, and 4x minus 5y is equal to 20. And I'm just making these up off the top of my head, so they may be really ugly. But the idea is I'd have to solve one of the equations for one of the variables, and it doesn't matter which one. So if I look at 2x plus 3y is equal to 6, and let's just say we're going to solve it for x. So I'd have 2x is equal to negative 3y plus 6, and then dividing by 2 gives me x is equal to negative 3/2 y plus 3. Now my second step is to plug that into the other equation. So in place of x, I'm going to put the negative 3/2 y plus 3. So we would now distribute to get 4 times negative 3/2. What that goes in there 2 times. 2 times negative 3 is negative 6y plus 12 minus 5y is equal to 20. So negative 6y minus 5y is negative 11y plus 12 equals 20. We can subtract 12 from both sides to get negative 11y is equal to 8. So y is negative 8 over 11. Okay. Now we have to solve for the other variable. We need to find out what x is. So we can go to either one of the 2 original equations and find out what x is in this way. So if we use 2x plus 3y is equal to 6, we'd have 2x plus 3 times negative 8 over 11 is equal to 6. So 2x, go ahead and multiply here. 3 is really over 1, so that's minus 24 over 11 is equal to 6. Now if you don't like the fractions, we can multiply through by 11, which is the LCD, to get 22x minus 24 is equal to 66. So if we add 24 to both sides, we would get 22x is equal to 90. So x is 90 over 22, or we can reduce that down to 45 over 11. So the solution here would be 45 elevenths and negative 8 elevenths. Okay, so we've learned another method to solve systems. In the next lecture I will talk about yet another algebraic method to solve systems. So if you have any questions, please don't hesitate to contact me. Thank you.